Yeah, so we have seen these questions. Halting problem, Hilbert's, or well, we have not seen it, but we will do it in kind of chapter 1, halting problem, Hilbert's 10th problem. In chapter 2, we'll introduce this PNP problem. In chapter 3, we will introduce P space versus P space versus NP problem. Okay. Next will be formula optimization. Okay, what is this problem? So this is the simple question of smallest formula. Okay, you are given phi in this formula representation. Can it be made smaller without changing the value? So given a formula which will be, mind you, Boolean formula. Decide whether there is a smaller formula psi which equals phi. Now, what does smaller mean? Smaller in terms of what? Well, smaller in terms of size, right? The variables cannot change obviously, because you want psi and phi to be, actually even the variables can change, right? It may happen that for example, let's see this. So it may happen that you have something like x1 or x1 bar, right? This is a formula, but this is always true. So this can be replaced by 1. Right? So you don't need this long expression x1 or not x1. You can just simplify it to 1. So in that sense, can phi be simplified? Can phi be simplified to a smaller formula psi? So this will raise the question and define a new complexity class called PH, polynomial hierarchy. And the question will be whether polynomial hierarchy is different from NP and P. Okay, let me write. So PH, whether it is different from NP, different from P. Okay, these will be the new questions and a new complexity class. And we'll show that this formula optimization sits right there in PH. Fifth is the question of identity testing. This will be an interesting one because the only algorithm we know, fast algorithm we know for this is randomized. Okay, this will be an application of randomness. So what's the question? The question is given polynomial in n variables, decide whether f is 0. Whether this polynomial is actually identically 0. Okay, x1 to xn are actually, think of them as formal variables. This is actually a practical problem, and there are practical solutions which just randomly select x1 to xn, but there is no de-randomized version of it. So, the question and the class that this problem will introduce is BPP and whether it is bigger than P. In other words, can randomized algorithms, fast algorithms, be de-randomized in a fast way? Okay, that will be the main question here. In fact, conjecture is that P is equal to BPP. So, let me put that as the question, whether P is equal to BPP. In other cases, conjectures are that these classes are different. Okay. Next is the question of on graph reachability. So, as the name suggests, you are given a graph, you are given vertices, two vertices, source, target, whether there is a path. That's what you want to test. Given graph G and vertices S comma T, and very little computing space. Very little workspace, computing space. Okay, so the input is big with respect or in comparison to the computing space. That's very, very small. Think of it as exponentially smaller. Can you find a path? Can you decide whether there is a path? So, decide whether there exists a path S to T. Okay. So, say the graph size is n, then you can use, if you have done algorithms, you know that this reachability problem can be solved using depth first search or breadth first search. That is how you do it in practice. But then that requires how much space? N space. If you do the analysis, the time is linear and the space is also linear. But now here you are being asked to reduce the space requirement, minimize it. Okay, so this will show that actually it can be done in log n space, logarithmic in the input size. Workspace can be very, very small, minimum possible in fact, you can really optimize. And the question it raises, the complexity class it gives is whether L is equal to RL. Okay, we'll fancy L. So, this fancy L is the complexity class of problems that can be solved in logarithmic space, and RL is the randomized version of this. Problems like graph reachability will show is there. Okay, there is a randomized log space algorithm. So, are these classes the same? Again, the conjecture is that they are, but we don't know. These are open questions. Next is permanent. So, permanent, if you have heard of determinant, permanent is a sibling of determinant, right. So, for a matrix, it is defined for a matrix. Given matrix A, n cross n square matrix, let us say it has integral entries, rational entries, compute its permanent. What is the definition? So, in the case of determinant, what do? You take the product of entries in A and then sum it up over permutations, right. So, what you do is you take a product of A I pi I. You multiply these entries and you'd sum it up for every possible permutation. So pi is a permutation on 1 to n. So determinant, there would have been a sign here, sign depending on the permutation pi, but that sign we have put here in the case of permanent to be 1. Okay, that's the difference. So if you put sign to be the sign of permutation pi, then you get determinant. Okay, but if you make all the signs equal to 1, then you get a different function, and that function is called permanent. And permanent is a very important function. Also, in practice, it is very important because we'll see in this chapter that it somehow is computing, asking the question, how many satisfying assignments are there? Okay, so it is the counting version of SAT. That's why it is very important. It's actually, then you expect it to be even harder than SAT. And the question that it raises is, we'll define these complexity classes. Complexity class sharp P. Okay, sharp P is where this counting of satisfiability happens. This sharp is referring to counting. And FP is referring to functional problems solvable in polynomial time. So this is exactly the question whether permanent can be solved. Permanent can be computed, right? Here you actually want to compute the function. So this is different from decision problems. In all the previous problems you were talking about yes or no answers. But now here first time we are asking for value, not just yes, no. Okay, next is graph isomorphism. So given two graphs, G1, G2, decide whether they are isomorphic. Okay, whether the two graphs, given graphs, are isomorphic. Isomorphic means what? Again, isomorphic means that they find a permutation on the vertices, a relabeling on the vertices, such that on that, for that relabeling, G2 becomes equal to G1. Okay, equal meaning the connections, the edge connections will look exactly the same. Okay, so natural question. It's a very important practical question. So this question is so important again as all the previous questions, problems. This is so important that it spawned many new complexity classes. Okay, so the complexity class that this guy spawned is IP, interactive protocol, and whether that is equal to polynomial time. Okay, so this problem actually inspires a complexity class and then immediately a question whether this complexity class is different. So if you can show, I mean, the question, open question is whether there is a polynomial time algorithm for graph isomorphism. And it's important to mention that after decades of this question being completely open, significant improvement was obtained few years ago. So what happened is in 2016, Babai gave a breakthrough showing that GI has a, so let me call this graph isomorphism problem GI. So GI has two raised to polynomial in log n. Okay, some absolute constant, universal constant C, this much time algorithm. Okay, so this was a real breakthrough. It's what is called quasi polynomial time algorithm. It's not yet polynomial time because it's not polynomial in n. This function is actually super polynomial in n. It is something like n to the log n, but it is also not exponential time. So it's somewhere between polynomial time, exponential time, more towards polynomial time. So this can potentially be a practical algorithm someday. That's a major area, graph isomorphism. We'll touch that. Yeah, so that completes the overview. These are the problems we'll be focusing on and the complexity classes. And the relationship between these complexity classes is what we are interested in. Whether these complexity classes are different, whether one is contained in the other, and yeah, something called oracle also we'll study. So using one complexity class, which other problems can we solve? Can we use a complexity class as an oracle, right, as a subroutine? So a lot of these connections we'll see in this course and prove them. So you can, if you want, you can look at earlier offerings of the course. So you can go to my home page, and under teaching you can find earlier versions and related courses that I have offered and taught. Okay, under users Nitin. So yeah, so under teaching you can find all the courses and their slides and their lecture notes. If you are registered in IIT-K, then I should give you the grading policy. So the grading policy is there will be assignments. So assignments, I plan to give you maybe 4 assignments, and there will be a mid-sem exam and end-sem exam. So assignments weightage we can have say 40%, and midsem and endsem we can have each 30%. Okay, so that you will have many opportunities. Assignments will force you to learn the chapter, and midsem and endsem will test more and above the assignments. Yeah, so that is the overview and the policies. Finally, since I defined so many complexity classes, I should also tell you how they are possibly related, all of them together, right? So let me draw that picture. So the current status of classes of the classes. So this log space is contained in RL, but we don't know whether they are equal. RL, which is randomized log space, that is contained in P. We don't know whether they are equal. If they are equal, it will be very surprising, because that will mean that any polynomial time algorithm can also be run on log space using random bits. That will be surprising. So we expect them to be different, but we don't know for sure. Then obviously the most important question could be this: P different from NP, but P is contained in NP. Similarly, NP is contained in the polynomial hierarchy, but we don't know the proof whether they are different. Polynomial hierarchy is, I will not define what P raised to sharp P is, but just think of it as sharp P. So polynomial hierarchy in some sense is contained in sharp P, but we don't know whether they are different, whether the right hand side is bigger. Okay, but we expect it to be bigger. And this is, we expect this to be different from IP, interactive protocols, but it is certainly, we'll show that it's contained in IP, but we don't know whether they are different. We'll show that actually, for a change, we'll show that P space and interactive protocols are the same. Okay, this is a famous theorem, IP equal to P space. This we'll show. And we don't know whether this is, P space is contained in exponential time, but we don't know whether they are different. However, what we do know is P and, okay, let me branch this off. We don't know whether P and BPP are equal. Okay, so P is contained in BPP, but we don't know whether they are equal or unequal. We conjecture them to be equal. And finally, we actually know that P and exponential time, polynomial time, exponential time are different. Okay, so we have kind of gone full circle. We started with polynomial time and we keep increasing it, keep getting bigger and bigger complexity classes, but we are not for sure, we are not sure that they are really bigger, but we conjecture. And in the end, this exponential time we know for sure is different from what we started with, which is P. Okay, so that is a quick overview of all these complexity classes, how they relate, and what is not known. Essentially, all these connections are currently open questions. Okay, so for now, these are only keywords for you, but just you can remember this picture. This is what we'll be working towards throughout the course. Okay, so we have some time left. We can now start the formalization of problems. Formalize problems and inputs. So what is a problem and what is an input in computer science for computers. So, a problem for us would always mean computing a function. Computing a function whose input and output are finite. Are finite Boolean strings. Okay, so this finiteness is the key thing here. So, it is a function so I can write this as a function f 0 1 star to 0 1 star. Okay, it's a function that we are trying to compute which takes a string and gives out another string. So, this we can call multi-valued Boolean function. Okay, because it is kind of giving many bits in the output. So, it is multi-valued, but we can also look at functions and they are equally interesting which only output a single bit. So, you can think of it as true, false, yes, no, okay, 1 bit output. But this is the most general thing you can do in computer science, that you map strings to strings, right, and see how fast can you do this. In particular, our problems are not continuous problems; they are very discrete. Okay. All continuous problems you have to discretize before you can use on computers. So, this captures almost all math functions as we can express integers, so integer, let me say, if you have an integer x or if you have a graph G, or if you have a vector V, matrix A, or some ring arithmetic, ring R. It all these mathematical objects, rings, fields, vectors, hence integers, then over that matrices, graphs, you can represent them in bits, right. So, unless there is this continuity issue like complex numbers, transcendental numbers like e, pi or square root 2, they require infinite information, but usually these math objects which are which have finite representations, you can convert them into bits and then give as input, and your algorithm or your function will give these things as output. Okay, so this makes sense. Why do we focus on bits? Well, because 0 1 is kind of off on, right. 0 is kind of off, 1 is kind of on in electronic circuits. Inside computers. That is a simple reason. So we focus on bits so much because computer stores everything in terms of uh, absence of current or presence of current, so off or on. And so that is all you can do. Everything you have to reduce to this and then run your clever process called algorithm or computation. What is, as I mentioned, what is also interesting are decision problems. So usually functions have meaningful Boolean or decision versions. Okay, example, I mean that is decision version or Boolean version means function which is outputting only 0, 1. Right? Usually we think of this as yes, no. So decision problems, many, I mean, when I gave the overview, many problems were just decision problems, 1-bit answer. And functions can be actually reduced to meaningful decision problems. And that is what we'll use to define complexity classes in the next class.